All right, today we are going to dive into one of the most fundamental and frankly, totally mind-bending concepts in all of physics. It's this principle that underpins, well, everything, from the energy blasting out of a star to the very existence of your own hand. We are talking about symmetry.
So when I say symmetry, what pops into your head? Probably something like a butterfly's wings, right? Or maybe a perfectly balanced building. It just feels aesthetic. It's pleasing to the eye. But what if I told you that in physics, symmetry has almost nothing to do with beauty? What if it's actually the absolute non-negotiable requirement for reality itself to even make sense? Yeah. Okay, let's get into it.
See, for the longest time, the common sense view was that symmetry was just a nice feature of the universe, kind of like an aesthetic choice that nature just happened to make.
The old way of thinking went something like this. The laws of physics just happen to be the same today as they were yesterday, and they just happen to be the same here as they are on the other side of the galaxy. You know, physicists studied symmetric systems mostly because the math was cleaner, a lot prettier. But nobody thought there was a deep reason for it. It was just a lucky convenience. And then, a discovery came along that completely shattered that entire picture.
This all changed in 1918. A truly brilliant mathematician named Emmy Noether, she uncovered a connection so profound, so deep, that it just completely rewrote our entire understanding of the universe. Her discovery is now called Noether's theorem, and honestly, it is elegance itself. What it says is that for every continuous symmetry you find in the laws of physics, there is a corresponding thing, a quantity, that must be conserved. It's not a coincidence. It's not a choice. It is a mathematical necessity.
And just look at the implications here. I mean, this is breathtaking. The fact that the laws of physics don't change over time, well, that symmetry directly gives rise to the law of conservation of energy. The laws are the same everywhere in space, boom, that's where conservation of momentum comes from. And the fact that they're the same in any direction you look, that gives us conservation of angular momentum. So here's the kicker. All the stuff we think of as being so fundamental, energy, momentum, it isn't really stuff at all. It's just the shadow of a deeper geometric reality.
This discovery just forced physicists to flip the whole question on its head. We shouldn't be asking why the universe has all these beautiful symmetries. We should be asking why it must have them. Okay, let's try a thought experiment. Imagine two astronomers, right? They're both looking at the exact same distant galaxy. One of them is here on Earth, and the other is whizzing by in a super-fast spaceship. Now, they both measure the galaxy's energy and its momentum, but because they're moving differently, they get completely different numbers. So, are their observations inconsistent? I mean, is reality just subjective? No way. And the reason they can both be right is symmetry. You can think of symmetry as the translation manual. It's the shared grammar that allows observer A to take her measurements and translate them perfectly into observer B's language, and the other way around. Without this shared rulebook, they could never compare notes. Reality would just be a chaotic mess of disconnected viewpoints. Okay, so if symmetry is the grammar of reality, how does that grammar actually build the words in sentences? I mean, how does it build the particles themselves? Well, the logic is actually pretty amazing. Let's just start with a simple idea. Imagine the fundamental screen of reality is a sphere. Now, any law of physics you write on that sphere has to work no matter how you rotate it, right? It has to respect the sphere's rotational symmetry. Well, it turns out that this one simple requirement forces any fields living on that sphere to arrange themselves into very specific allowed patterns. You can kind of think of them like the allowed ways a drumhead can vibrate. These patterns have a name, spherical harmonics, and each one is labeled by a simple whole number, 0, 1, 2, and on and on. And that number, that's what we call particle spin. The geometry itself demands that spin must be quantized. It can only exist in these discrete whole number packets. And this is a really beautiful picture. I mean, it works perfectly. Particles like the Higgs boson have spin 0, the photon has spin 1, the graviton we think has spin 2. It all fits except for one massive problem. The stuff that you and I are actually made of. That's right. Electrons, quarks, all the fundamental building blocks of matter, they all have a spin of 1/2. But wait a minute. Our neat little geometric picture only allows for whole numbers. There's no spherical harmonic for 1/2, so how in the world can these particles even exist? It seems totally impossible. But this is where quantum mechanics pulls a very, very strange rabbit out of its hat. Let's actually try a little experiment right now.
If you can, just hold your hand out in front of you, palm up. Imagine you're holding a cup of coffee and you really don't want to spill it. Okay, now keeping that cup level, rotate your hand a full 360 degrees by bringing it under your arm and all the way around. Now take a look at your arm. It's all twisted up, isn't it? You've rotated a full 360 degrees, but you are very clearly not back where you started. All right, don't undo it from that twisted position, just keep going. Do another full 360-degree rotation in the exact same direction, bringing it under and around again. And would you look at that? Your arm just untwists itself. You're right back in the starting position. It took a full 720-degree turn to get back home. Your arm, in that moment, acted just like an electron. They're what physicists call spinors. And this bizarre quantum mechanically allowed property is the loophole in reality that lets matter exist at all.
So we're seeing that the universe is built on these fundamental rules of symmetry. But, a lot of them are hidden from us or broken in our everyday world. A great example is the Higgs mechanism. It actually breaks a fundamental symmetry to give other particles their mass. So in a way, we're living in a kind of frozen shard of a much more symmetric reality. But there is one combined symmetry that, as far as we know, can never ever be broken.
It's built from three fundamental transformations. First, you can swap a particle with its antiparticle, that's charge, or C. You can view the world in a mirror, that's parity, or P. And you can run the movie of events backward, that's time, or T. Now, here's the wild part. Experiments have shown that nature actually can and does break each of these symmetries all on their own.
But, and this is the really crucial point, if you do all three of those things at once, C, P, and T, the laws of physics must remain unchanged. This combined CPT symmetry is thought to be absolute. It's like the non-negotiable consistency check for the universe. It's the reason a particle and its antiparticle are guaranteed to have the exact same mass and lifetime. It really is the one rule that can't be broken.
So we're left with this just incredible thought. The universe that we see and experience every day, with all its specific forces and particles, is really just one possible state. It's a frozen configuration where many of the universe's deeper, more primordial symmetries are hidden from our view. It really makes you wonder, doesn't it? What would reality look like if we could somehow unfreeze it all and see it in its original, perfectly symmetric form? What are we missing?